So let's look at the Laplace transform of an exponential of mod t. And we've got minus b in the exponential for positive values of b. So I always like to start by drawing a plot of the function that we're looking at, and in this case here, a function of time. And for positive values of t, it's e to the minus bt, looks like this. And for negative values of t, well, they get the modulus of those, and so it's this symmetric function. So this is the function here, and once we look at this, I think we can see that this function is made up of two other functions that we know about, and it helps to write them down. So xt equals, in fact, e to the minus bt times u of t. This is the positive time portion, plus e to the minus b, sorry, e to the positive bt times u of minus t, and this accounts for the negative portion. Okay, and once you see this, this function here is something that we know about, is a very common function for Laplace transforms, so I'm not going to work it out here, but to work it out you use the same steps as I'm going to use for this one. I'm going to do this one slightly harder just to make sure that everybody understands the steps. So the real part of s has to be bigger than minus b for this term here. And so let's actually evaluate this one here. So if we try to evaluate this one here, so that we're confident everyone knows the steps, this is the step function in the negative direction, so the Laplace transform would be the integral from negative infinity to 0 of the term e to the bt, and the Laplace transform is times e to the minus st to t. And so to do this, we've got exponential of b minus s times t, and so this will equal 1 divided by b minus s times the exponential of b minus s times t, evaluated between negative infinity and infinity. And so when we put this term in here, e to the 0 is of course 1, so this gives us equals 1 divided by, and I'm just going to write s minus b instead because we commonly put the s on the left hand side, so this is the term from here. And then we can see this other term, for this to converge, when we put negative infinity, we have to have only for values where the real part of s is less than b, and that will ensure that everything in the exponential is negative. So you want this term here to be positive because it's going to be multiplied by negative infinity. Okay, and that will be overall negative infinity, which exponential of negative infinity is 0. So this will be the term, but only holds this other element here of the integral. This other limit only holds for the real part of s less than b. Okay, so hopefully you can see that the real part of s has to be less than b for this to be positive. It's going to be multiplied by negative infinity, which gives you a negative exponential of negative infinity exponential, which is equal to 0. And so this converges. If this was the other way around, you'd have e to the positive infinity, which is of course infinity, and therefore you don't have a defined function. Okay, so this means our overall function x of s equals 1 divided by s plus b, plus this term here, which is minus 1 divided by s minus b, and it only holds together when both of these regions of convergence are satisfied. So this says that the real part of s has to be bigger than minus b, and this says the real part of s has to be less than b. So this region of convergence is in the middle. I just move down here. So this region of convergence on the sigma and omega plane, but don't forget s equals sigma plus j omega, and so this one says it has to be less than b, and this one says it has to be bigger than minus b. And so for all values of s, which are between these two limits, this function holds. And this, you can collect the terms, multiply by the two, put them on the same denominator, and you can get minus 2b divided by s squared minus b squared.